This is IAT806, Lecture 11, and in today's session we're going to talk about three algorithms for doing fundamental things that pretty much every computer program needs to do once you're dealing with a decent amount of information. The first thing we're going to talk about is binary search, then we're going to talk about sorting, and then a variant on sorting, the most efficient algorithm in general, something called quicksort. So the next segment is, in this segment we're going to be talking about binary search. So I had talked in a previous lecture about building a data structure to do searching, namely the binary search tree, but I hadn't really talked about what algorithms or what work do you do if you have your data in a collection such as an array or an array list. It's still possible to do rapid searching in an array or an array list, and instead of organizing the data with nodes and pointers, what you do is use an algorithm to grapple with the problem of how to locate things quickly. And you frequently want to organize your data to support search. And as I'm sure you'll understand as we move forward through these lectures, lecture segments 1 through 3 of lecture 11, you'll notice that for both of these approaches, building a data structure like a binary search tree or creating a list, an array that makes for easy searching, you have to do some advanced preparation. So the typical tasks that you want to be interested in are things like searching for a single item. You know, you've got a particular name and you want to find it in the data set. Another variation is to search items within a range. Both of these things require that you locate, you know, the item or the suite of items that are in that range, and they both require searching. Okay, so you often want to search items in a list, in an array, as I mentioned already, and in an unsorted list, and that's shown up above, this one right here, you must search linearly because you don't know anything about the list. It seems like it's in random order. It might be in some order that we don't know, but it's not useful for searching in this formulation. So what you need to do is just simply investigate every item from first to last. And if you have a million items, that means you have to do a million queries in some sense, a million investigations of each item as you move along the array, and that's not very efficient in terms of time. It consumes a lot of time to do that. However, in a sorted list, as shown here, this is the same number of items that are just simply put in sorted order down below. You can do it a lot faster. So let me show how that's done. So the standard method for dealing with doing search in a sorted list is that you know something very special about the way the list is organized. Of course, it's in sorted order, and what that means is that every item in the list, for every item in the list, all the items before it are less than that value, and all the items after it are greater than, or perhaps greater than or equal to, but here we have unique values. So they're greater than. So to the left of 12, we have 4, 5, 9. They're all less than 12. To the right, we have 15, 26, 31, 62. And because you know that, that's useful information that will help cut down the amount of time it takes to search things very significantly. So the way in which binary search works is you have two indices, one pointing at the start of the list and one pointing at the end of the list, and those two indices are meant to indicate you know, the range over which you have to search. You then just mathematically compute the sum of those two divided by 2, and that gives you the midpoint, right? That's the middle element. That's the one that's halfway between those two. You then query, is that element less than, equal to, or greater than the one I'm looking for? And you can probably guess about what happens next. So you compare that middle item to the search item, and if the search is less than, the thing you're looking for is less than the middle item, you change the end pointer to point at the item before mid, because you've already eliminated mid and everything above it from the further investigation. So now start and end is just these three items. You compute the new midpoint, and you compute the new midpoint, that points at the number 5. You investigate, is the thing I'm looking for less than, equal to, or greater than 5? So that is essentially how binary search works. And like searching in a tree, binary search takes a very short amount of time compared to the number of items that you have to deal with. With a binary tree, if you have a balanced binary tree, it's the logarithm base 2 of the number of items in the tree. And it's the same kind of thing here, because each decision that you make in terms of querying less than, greater than, or equal to at the midpoint, you cut out half the items of the list, and then half the items out of that half, and then half the items out of that quarter, and then half the items out of that eighth, and so on, until you get the thing you're looking for, or you return that it's not there, that you don't find it. And so what that means is that the amount of time it takes to search, say, 1,000,000 items is log to the base 2, logarithm to the base 2 of that size, 1,000,000. And so that's roughly about 20. That's really, really fast. You know, you are thinking 1,000,000, maybe it'll be, you know, 250,000, but no, it's 20 searches that you have to do, because you're cutting from 1,000,000 to 500,000, 250,000, 1/8,000,000, 1/16 of a million, which is roughly about 80K. Don't quote me on that number. 80K, 40K, 20K, 10K. You can see how that number is getting, you know, as you chop it in half each time, it'll get you down to 1 very, very quickly. So that's how binary search works. And one of the things that is kind of amusing in a, you know, second-year computer science class is to hand out exams and then, you know, make sure, tell everybody that it's sorted order, and you'll find that people will just run up to the, you know, and look in the first pile, and then the second pile, and the third pile, and the fourth pile, and I keep saying, binary search, people, binary search. Sometimes it works. Anyway, you can, each person coming up to get their exams out of the big separate piles, if they're sorted alphabetically, can find where their stuff is very, very quickly. So here's what the algorithm looks like. I just bumped ahead there for a sec. We initialize an integer array with 8 elements in it, and the thing we're searching for is 4, right? That's the integer we're searching for. And then we set the integer for the first element of the array to be start, to be 0, and set the end pointer to be array.length -1. Right, because we wanted to actually point at the last element. So because array length is the number of elements, it goes from 0 to the number of elements -1 for indices. And then we have the third value, mid. And then you just simply say mid equals start plus n divided by 2. That, you know, rounds to some integer value. And if search, the thing I'm looking for, is equal to the item at array square brackets mid, then success, and we're done just like before. And you typically would get out of this loop. If search is less than array.mid, n equals mid -1. Otherwise, start equals mid +1, because we've eliminated mid from further inquiries once we found it was not equal to the thing we're searching for. So a very short algorithm does things very, very quickly. Okay, so as I mentioned earlier, the runtime for this thing is very quick. It's log base 2 of n, where n is the number of items. And the reason why it does this is because it chops every item, chops the list in half. It doesn't actually cut anything. It just simply reduces the size of things by half that it has to look at. Slightly greater than half, you know, because it's the middle item you're eliminating every time. So that's it for lecture segment 1.1. I wanted to just separate the chunks of this lecture into separate segments that are about separate algorithms, so you can focus on how those algorithms work. So that's it for that.